we're asked to consider the function f of x comma y over the region defined here, where y is on the closed interval from 0 to 2, and x is on the closed interval from 0 to y cubed. So the region we're considering is this region here, graphed on the xy coordinate plane. We're asked to evaluate the given double integral over the region D. Let's first take a look at this graphically. The graph of our function f of x comma y is graphed here in blue. The region of integration is this region here, and notice how because the blue function is non-negative over this region, our double integral is going to give us the volume bounded by the surface in the xy plane over the region of integration, which would be the volume of the solid in here below this blue surface. So going back to our work, let's set up our double integral. Notice how they do tell us we need to integrate first with respect to x, then with respect to y. So we know the integrand function is e raised to the power of x divided by y. We'll first integrate with respect to x, then with respect to y. When we get with respect to x, we're integrating from left to right along the xy coordinate plane, which means we're going to start integrating here on the far left and stop integrating here along this curve. We'll notice how this vertical line would be x equals 0, which is a lower limit of integration for x. And then because this curve we know is x equals y cubed is going to be the upper limit of integration for x. Integrating with respect to y, we'll first start integrating here at y equals 0 and stop integrating here at y equals 2. So for y, we integrate from 0 to 2. Now that we have our double integral, let's evaluate this on the next slide. Integrate with respect to x, we treat y as a constant, but notice how the exponent here is x divided by y. So we'll have to perform u substitution. We'll let u be equal to x divided by y.
And differential u is equal to the derivative of x divided by y with respect to x times dx, which would be 1 over y times dx. Notice how we don't have 1 over y in the integrand, so if we multiply both sides by y, we have y differential u equals dx.
So to help us find the antiderivative, let's rewrite this in terms of u. This would be e to the u, but dx is equal to y differential u. So we have a factor of y as well as differential u. So if we integrate with respect to u, we treat y as a constant, so we'd have y times e to the u. So if we integrate with respect to x, we would have y times e to the x divided by y, since u equals x divided by y. And now these limits of integration are for x, so we'll perform substitution for x with y cubed and 0, and then find the difference. So when x is equal to y cubed, we would have y times e raised to the power of y cubed divided by y, and then minus, when x is 0, we'd have y times e raised to the power of 0 divided by y. And simplifying, here we have y times e raised to the power of y squared, and then minus, here we just have y times e to the 0, which is y times 1, so we just have minus y. Let's go ahead and break this up into two separate integrals. We have the integral from 0 to 2 of y e to the y squared, and then we'd have minus the integral from 0 to 2 of just y. This will be helpful because we do have to perform u substitution to find this antiderivative here. Notice here if we let u equal y squared, then differential u is going to be equal to 2y dy. We have y dy here, so let's go ahead and divide by 2. So 1/2 differential u is equal to y differential y. So in terms of u, we can rewrite this as, again, y dy is equal to 1/2 du, and this would be just e to the u. So the antiderivative in terms of u would just be 1/2 e to the u. So if we integrate with respect to y, we would have 1/2 e to the y squared. And the integral of y would just be y squared divided by 2, or 1/2 y squared. Let's go and evaluate this on the next slide. Of course, because our limits of integration are the same, we can also just write this as 1/2 times, and then we'd have e to the y squared minus y squared. Let's go and evaluate in this form. So we have 1/2 times, when y equals 2, we'd have e to the 2 squared minus 2 squared, minus when y is 0, we have e to the 0 squared minus 0 squared. Simplifying again, we have 1/2 times, this would be e to the 4th, this is minus 4, and then here we have e to the 0, which is 1, so minus 1, and of course that's 0. So the exact value of the double integral would be 1/2 times the quantity e to the 4th minus 5, and as a decimal approximation, this would be approximately 24.7991, which again, because our function is non-negative over the region of integration, this is the volume bounded by the surface in the xy plane over the given region. So if we go back to our graph one more time, here we're looking down on the region of integration here. If we change the view, we just found the volume below this blue surface above the xy plane over this region here. Okay, I hope you found this helpful.